Hi folks, Astronomy Live here. Going to be talking today a bit about Venus as seen from stereo head HI2, seen in these images, and that strange object off to the left one more time. We're going to take a look and see if the motion of Venus is normal, and then we're going to take a look at the object that always appears every time Venus reaches this point in the images, and see if it's even physically possible for it to be a physically real object in space. So here's what Thor's been saying about this recently.
Hey, why ain't Venus moving? How come Venus has been in the shot for like a month? That don't make no damn sense whatsoever, bro. None. But hey, what is that? Why is it acting like that? Why are those lines coming out? You know?
Okay, so first, real quick, we'll address the vertical line seen passing through Venus in this image. That's normal CCD blooming. It happens to bright objects and some CCDs when an object is overexposed. The electrons will spill over onto neighboring pixels along the same column and produce a vertical streak. Here's another example of that from a different telescope, one that has a spider vane as seen by the diffraction spikes. But you can see how those diffraction spikes are distinctly different than the vertical CCD blooming spike passing through the star. That spike is solid white all the way up and down, and that's because in order to spill over into the next pixel along the same column, it has to completely fill the previous pixel. So now the next question we'll address is why does Venus appear to be moving so slowly from stereo head HI2? Well, let's take a look and find out. For this part, I'm going to step in front of the camera and show you all how you can calculate where Venus should be from the perspective of stereo head for yourselves. This part's going to involve a lot of math, and it'll take about 17 minutes to go through it all. If that bores you and you don't want to watch it, no problem, just click the annotation and skip to the results. Alright, so we want to know how quickly should Venus be appearing to move from the perspective of stereo head on the HI2 camera. Now the HI2 camera has a very wide field of view, about 70 degrees wide. So we don't need super high precision, but we want to know approximately to within, say, half a degree. Where is Venus in the field of view of the HI2 camera, or is it in the field of view at all? Should it be moving out of the field of view much faster than it is? Well, we're going to answer that. We're going to answer that by calculating it directly based on the orbit of Venus and the orbit of stereo head. We'll use two-body methods, which are the same approximations used by the Java applet out on the JPL website for minor planets. If you load up an orbit of an asteroid on that Java applet that shows you a diagram of the orbit, it's using two-body methods. That's a good enough approximation for a situation like this that doesn't involve a planetary encounter circumstance or integrating the orbit over a very long time, say 50 years or more. So for that, we can use two-body methods. We'll also approximate a solution for Kepler's equation using just the equation of center. These are very circular orbits for both Venus and stereo, so we can get away with that. If it were a very eccentric orbit like Pluto, that wouldn't work. So we need to know what the orbital elements of stereo head and Venus are. Now for Venus, I'm going to provide a scanned page out of a book I have that has the mean orbital elements of Venus for the date of 1990, and we're going to use that to calculate the position of Venus for stereo. I have the orbital elements from January 1st, 2014, and I'll provide that in the video description as well. The number of days since Epoch. For stereo and for Venus, it's going to be a different number because the orbital element Epoch is different. But we're going to calculate all of this for an observation date of August 8th, 2014, at a time of 9 minutes 21 seconds universal time, 00 hours 9 minutes 21 seconds universal time. And that's because that will be the date of observation for the first picture I'm going to show you from stereo ahead. So first thing we need to do is calculate the mean anomaly. And I've written the formula for that up here. The formula is 360 divided by 365.242191 times the number of days since the epoch of the orbital elements. Again, for Venus, that will be 1990, and for stereo, that will be 2014, divided by the orbital period. For stereo, that's 0.943336992, plus the longitude at the date of epoch, which in stereo's case will be 251.3209373 degrees, minus the longitude at perihelion, longitude of periapsis, in this case perihelion, which for stereo head is 308.4127956 6 degrees. And that will give you the mean anomaly. Now you need to calculate the true anomaly. But we're just going to use the equation of center as a way of solving Kepler's equation to get the true anomaly. And the equation of center is the mean anomaly plus 360 divided by pi times the eccentricity times sine of the mean anomaly. Then from there we can calculate the heliocentric longitude. And the formula for that is 360 divided by 365.242191 times the number of days since epoch divided by the orbital period in years plus 360 divided by pi times eccentricity times the sine of the mean anomaly. And that will give you the heliocentric longitude. Then we calculate the radius vector, the distance from the sun, essentially. And that will be the semi-major axis, abbreviated by lowercase a, times 1 minus eccentricity squared, divided by 1 plus eccentricity times the cosine of the true anomaly. Now we need to calculate the heliocentric latitude, which will be the arcsine of sine heliocentric longitude minus longitude of ascending node times the sine of the inclination. And then we're going to need to calculate the heliocentric latitude projected onto the plane of the ecliptic, which will be calculated by the arctangent of sine of the longitude, heliocentric longitude, minus the longitude of the ascending node times the cosine of inclination, all divided by the cosine of the heliocentric longitude minus the longitude of the ascending node plus the longitude of the ascending node. Now, there's a bit of a pitfall here. If you're not careful, you could make a mistake because of quadratic ambiguity. So if you use the a tan2 function in your spreadsheet program, it will evaluate the nominator and the denominator separately, and it will automatically place the angle it gives you into the correct quadrant. Then we need to calculate the radius vector projected onto the plane of the ecliptic, and that is given by the radius vector times the cosine of the heliocentric latitude. So you do all that for stereo. Then you do all that again for Venus. And what you end up with is the ability to calculate the stereocentric, normally it would be geocentric, elliptical longitude and latitude of Venus. But in this case, it's stereocentric. The coordinates, the elliptical coordinates of Venus as seen from stereo. And the elliptical longitude, I'm going to erase all this to make room, is given by the formula. We're going to abbreviate it as lambda. The answer is lambda. 180 plus the longitude, the heliocentric longitude projected on the plane of the ecliptic of stereo, which I will abbreviate as L sub s prime, plus the arctangent of the radius vector of stereo projected onto the plane of the ecliptic times the sine of the heliocentric longitude of Venus, sub V we'll call it, prime, let's see, minus, we'll call this one L sub s, L sub s prime again, the heliocentric longitude of stereo projected onto the ecliptic, all divided by the radius vector, again, of stereo projected on the plane of the ecliptic. Hello, new me realized that old me made a mistake at this point. Now all these calculations were done ahead of time, and they were all done correctly, so the numbers given at the end are correct. I used an Excel spreadsheet to do all the calculations, which will be available as a link in the video description. But let me give you the correct formula for this portion. The denominator of this arctangent function should be the radius vector of stereo projected onto the plane of the ecliptic minus the radius vector of Venus projected onto the plane of the ecliptic times the cosine of the heliocentric longitude of stereo projected onto the plane of the ecliptic minus the heliocentric longitude of Venus projected onto the plane of the ecliptic. And now back to old me for the rest of the equations. The correct quadrant for that. So then we need the stereocentric ecliptical latitude. We'll abbreviate that as beta. And that will be given by arctangent of the radius vector of Venus projected onto the plane of the ecliptic times the tangent of the heliocentric latitude of Venus, that is phi sub v, times the sine of lambda, this guy, minus the heliocentric longitude of Venus projected onto the plane of the ecliptic, all divided by the radius vector of stereo projected onto the plane of the ecliptic times the sine of the heliocentric longitude of Venus projected on the plane of the ecliptic minus the heliocentric longitude of stereo projected onto the plane of the ecliptic. And that will give you beta. So, in this case, for August 8th, 2014, lambda will equal 347.9021578 degrees, and beta will equal 0.60259348 degrees. Now, of course, we don't actually have this many sig figs to work with, not this many significant figures, because we aren't calculating for the perturbations of the planets. We're using a simplified method to simplified approximation for the solution of Kepler's equation. But these are the numbers you should basically come up with when you plug all this in. Then we need to convert these numbers to right ascension and declination. And so for that, we need to know what the obliquity of the ecliptic is. Right now, that number equals 23.43738 degrees roughly, and we'll call that OBO. Now, we just need to convert these to right ascension declination. So the variables are lambda, beta, and OBO for the obliquity of the ecliptic. So right ascension, RA, will equal the arctangent of sine of lambda times the cosine of the obliquity of the ecliptic, OBL, minus the tangent of beta times the sine of the obliquity of the ecliptic, OBL. I'm running out of space. Should have started that further over to the right. Okay, all divided by the cosine of lambda. Do the ATN2 function in your spreadsheet on that, and you will get an answer of 348.6385016 degrees. If you convert that to hours, minutes, seconds, you get RA, right ascension, equal to 23 hours, 14 minutes, and 33.24 seconds. Okay? Now for declination. Declination is given by the arc sine of sine beta times cosine obliquity of the ecliptic, OBL, plus cosine beta times sine OBL times sine lambda. And if you run those numbers, you get declination of negative 4.2226904723 degrees, which works out to negative 4 degrees, 13 arc minutes, 36.9 arc seconds. There you go. Right ascension and declination, approximately, of Venus from the perspective of stereo ahead on August 8th at 00 hours, 9 minutes, 21 seconds universal time. Give or take a fraction of a degree. So, you do that for August 8th, then you do that again for some other point in time. Say a month earlier or so. We're going to pick July 4th for our second point in time. I'm not going to run through all the numbers again, but now you know how to do it. So you do all this again for July 4th. The only difference now, you just plug it all in again with a different number of days since the epoch of each of the elements, and you get a second set of coordinates. Now we're going to project that onto the images from stereo head HI2 and see how far it should have moved, say, from July 4th to August 8th. And we'll see what we see. All right, so I've astrometrically solved the image from stereo head HI2 for August 8th, 2014 at 0 hours, 9 minutes, 21 seconds universal time, and plugged in the coordinates that we just found. And you can see that in the window on the left there. And you can see the green circle encompasses Venus's detected position. So those coordinates agree with Venus's detected position to within half a degree. It's quite a good fit with the observed data. Here's a spreadsheet I created using the formulas I just described to calculate the apparent position of Venus from stereo ahead, and you can see on August 8th it gives the coordinates that we just used. I also used the spreadsheet to calculate the apparent position of Venus from stereo ahead for July 4th at 0 hours, 9 minutes, 21 seconds universal time. Let's take a look at that image. I'll provide this spreadsheet as a link in the video description, and you can download it there and double check my work. So here's the image from July 4th with the coordinates that you just saw put into it, and you can see that it once again matches the detected position of Venus in the stereo ahead HI2 images, and you can also see the previously projected position from August 8th. And notice how very small the distance is between those points. Venus hasn't moved very much between July 4th and August 8th. It wasn't expected to. We calculated it mathematically ourselves using nothing more than the orbital elements of stereo ahead and Venus. And indeed, we find that this motion is completely normal. In fact, it matches the observations. Now you may be wondering, why is this? Why doesn't Venus appear to move very much from the perspective of stereo ahead? We know it's not supposed to. We just calculated that ourselves. But why? Well, let's take a top-down look here in Celestia and see if we can try to understand how Venus is moving in relation to stereo. You can see that in this view, the camera is moving with stereo A, so everything else is shifting or appearing to shift as stereo A moves around the sun. But it's really the camera that's moving with the spacecraft. But you can also see that Venus, although it's moving, it's only getting closer to stereo A during this time. It's essentially reached maximum elongation from the sun from the perspective of stereo ahead. And during that time, it doesn't move very much from a lateral perspective. It only moves towards stereo ahead. And that is why you don't see much motion from the perspective of stereo ahead HI2. Now that we've addressed the motion of Venus, let's go back and address that funny thing sitting off to the left side of Venus. As I discussed in my previous videos, this is a lens flare caused by Venus every single time Venus reaches this elongation from the sun from the perspective of stereo ahead. When it comes into the HI2 camera and it reaches about this point in the image, it starts generating that lens flare. And I do mean every single time. Here is every previous instance of Venus passing through the HI2 imager over the lifetime of stereo ahead. But some may ask, how can we really know that this is a lens flare? It's only appearing in the stereo HI2 imagers. Now there is another HI2 imager on stereo behind, and indeed it appears there as well. Now it's harder to see in this image, but this image was taken at the exact same time as the previous image I just showed you in 2009. And from the perspective of stereo behind, we see that same lens flare. Wait a minute, doesn't that mean it could be a real object in space? After all, it's appearing on two cameras at once, and the HI cameras were designed to monitor the space between the Sun and Earth. So couldn't it just be a real object in space that happens to be appearing whenever Venus shows up? Well, we can test that theory. So it's hard to see the lens flare in this version of the image from stereo behind, so I did my own processing of the raw data to bring out anything that wasn't moving through the images like a star, and you can see that here. Now we can see it much better, and do some measurements on it and figure out, could it be a real physical object in space instead of a lens flare? I also processed the stereo head image that was taken at the same time in the same way so that we have it available for direct comparison, because there's something a little off here and we need to measure it. Notice the angle that the so-called object makes pointing up towards Venus. It always points towards Venus every single time it appears. It also moves through the image as Venus moves. So because Venus isn't at the exact same point in both images in stereo head and stereo behind, if this is a lens flare, it could be pointing at two different angles, because Venus is not perfectly centered north to south in the image. So here I've measured it, and you can see that the so-called object is pointing up from horizontal by a little over 25 degrees in the stereo ahead image. But here comes the problem. It's not pointing at the same angle in stereo behind, even though that image was shot simultaneously. In stereo behind, it's only about 10 degrees from horizontal. These images were shot at the same time from the same orientation, only on opposite sides of the solar system. So if it were a real object in space, it ought to be pointing in a consistent direction, but it's not. The only possibility is that it's not a real object. It's simply a lens flare, and it always points towards Venus because it's being caused by Venus. That's all there is to it. Hope this video explained a lot for you, and have a nice day.